everyone, and welcome to the Joy of Abstraction book club, chapter 20. We're in the 20s. How amazing is that? Well, it has seemed like quite an epic journey, so I think that we should all feel very proud of ourselves. We have 24 fantastic questions for this week's chapter on functors. So let's get started right away because we've got quite a lot to go through. So let's see how many I can do at once before taking a break. We have great questions. Right, let's start. First question. Is any mapping from a category to set a forgetful functor, or is it just when the category is a set with structure type? Well, it needs to be set with something in order to have forgotten something. And so, for example, if it was a subcategory of the category of sets, that wouldn't be a forgetful functor. And so, for example, you could have a functor from the category of finite sets to the category of all sets, and that wouldn't be a forgetful functor because it wouldn't have forgotten. It wouldn't be the process of forgetting anything because you're starting somewhere with less stuff. Similarly, you could have a functor from the empty category to the category of sets. That wouldn't be a forgetful functor. You could have a functor from the terminal category. That's the category with one object and one just the identity morphism. You could map that into the category of sets, and that wouldn't be a forgetful functor. So that is the answer for that. Is it just when the category is a set structure type? No, because it might forget even more than that. So you could have a forgetful functor from the category of small categories to the category of sets, where you forget so much stuff, all you've got left is the objects. So maybe I should open the whiteboard at this point. So you could have a functor from the category of small categories to the category of sets. There are quite a few possible ones. You could forget to the set of morphisms. You could forget to the set of objects. But the most obvious thing to do, well, the thing I'm going to do, is to send a category C to the set of objects of C. So that I would say is very, because it's forgotten the morphisms as well. And that is a forgetful functor, but cat is not sets with structure, because the underlying data for a category is not just one set with structure, but it's two sets with structure. And so I would say that that's not a cat set with structure. Yeah, I think that's my answer to that. Next question. Could you give an example of a category that is not of the sets with structure variety? I think I just did. So that this one isn't sets with structure because it's more than a set with structure. You could also just have a category that simply is two objects and a morphism between them, and that isn't sets with structure because these are just objects and a morphism, so that's not a set. That those are not sets with structure. So remember, the objects can just be anything. They don't have to be sets at all. Is there a gradation system for how forgetful a forgetful functor is? Good question. So there isn't a formal one because there are so many different ways of being a forgetful functor. In a way, there isn't even really quite a definition of forgetful functor. It's more an idea than anything else. Certainly, you could put them in order if you can forget progressively if there are forgetful functors, but that's a kind of quick definition, isn't it? Because then you know what a forgetful functor is. But if you have something like rings, then you can forget the multiplication and get to groups, and then you can forget the inverses and get to monoids, and then you can forget the multiplication, and then you just have a pointed set because you have a set with a chosen object, which is going to be the identity, you just don't know it is yet. And then you have a forgetful functor down to set. So then, because these are all, this is a chain of forgetful functors, you could declare that these are a sort of hierarchy of forgetfulness. There's a concept of getting a property rather than a structure. So if you forget from groups all the way to sets, then you have forgotten what your binary operation is, and you're just a set. Whereas if you forget abelian groups to groups, then what you've done is you've forgotten the fact that you are abelian. So this is forgetting a property rather than a structure. And the thing is, if you forget that you're abelian, you're still abelian. You've just forgotten that you are. Whereas if you forget your binary operation, you're not a group anymore. And so I think that Jim Dolan coined this as senile functors because he said they're really, really forgetful. Because it's like if you I think his example was something like, if you go out and you forget your wallet, then that's just being forgetful. But if you forget that you are human, then that's pretty senile. And the thing is that if you forget you are human, you're still human. You've just forgotten it. Whereas if you forget your wallet, you haven't got your wallet. That's it. And so I think I seem to remember having a discussion with John Byers at one point about whether that is forgetting more things or not. Which one is forgetting more? Because if you forget your wallet, that's kind of less dire in terms of your mental state, but it's more dire in terms of the consequences. Whereas if you forget that you're human, it sort of doesn't matter because you still are. Anyway, that's that. The discussion about preserving and reflecting structure made me wonder, do functors have a notion of inverse? Well, what would the notion of inverse be? So the inverse is, you can always have a notion of inverse. Inside any category, there is a notion of inverse, because the inverse of something going like this is something going like that, such that if you compose that way around, you get the identity, and if you compose this way around, you get the identity. So yes, there is a notion of inverse for functor, because it's the inverse inside the category of categories and functors. So that means it's a functor going backwards, such that if you compose that way around, you get the identity, and you compose that way around and you get the identity. The thing is, it's not a very good notion. And the reason it's a very good notion is because it's unnecessarily strict. So if these are categories C and D, and you have a functor going that way, F, and a functor going this way, what does it mean for those to compose to the identity? So GF equals the identity. Well, where would it be the identity on? GF means do F first and then G afterwards. So that's the identity on C, means for all objects X in C, in C, G F of X equals the identity of X, which is X. Okay, see what has happened? There's an equal sign. I'm going to make it red. Can I make it red to point out that there is an equal sign in here? Uh-oh, that's an equality between objects of a category. That is too strict. Whenever we impose an equality between objects of a category, we should have these kind of warning signs blaring, saying, uh-oh, that's too strict. And so what that's telling us is that the notion of inverse for a functor is not a good notion, and a better one has an isomorphism here. And that's how we get the notion of a pseudo for functors and the notion of equivalence of categories. And I think that's coming in the next chapter. Right. Next. You've talked about pushouts of groups, but are there also pullbacks of groups? Yes, there are pullbacks of groups. And so there are, for good algebraic notions, there are typically products, limits and co-limits. And for products of groups, one thing we can look at is the fact that there's a forgetful functor from groups to sets. Now, we don't get this far in the book, but it's part of an adjunction. So the free functor is left adjoint to the forgetful functor. If a functor has a left adjoint, then it preserves limits, which means that we can tell what the product is going to have to be up here by going, if there were one, then when we applied the forgetful functor, then it would have to be the product of the underlying sets. And so we make the product of groups by taking the product of the sets and then lifting the binary operation on it. So when you do things like take R cross R and you do addition on it pointwise, so that you can take, say, a vector that goes X horizontally and Y vertically, and then you can add one that goes X primed horizontally and Y prime vertically, then what you get is you're going X plus X. So what we're doing here is we're making this product have a group action, have a group operation by doing the lifting the group operation in each component. This next question appears to be related to page 299, so perhaps I'll come back to that. Hopefully I'll remember. Okay, next question. You describe free functor as a kind of opposite of a forgetful functor. Is this related to duality or a sense in which free and forgetful are dual to each other? Yeah, so this is what I'm talking about, that it's adjunction, and we don't do adjunctions, but adjunctions are a pair of functors that are one step even less stringent than an equivalence. So it's still a pair of functors going in opposite directions, but it's not, they don't compose the identity. They don't even compose to isomorphic to the identity, but they have a kind of intimate relationship with each other. And so that they are kind of dual to each other. And the next question, I'm curious about functors that reflect rather than preserve structure. Do these forgetful functors reflect terminal and initial objects? Okay, so there's a whole load of questions here about reflecting structure. So let's think about the first one, which is posets to sets. Remember that the terminal object in set is any one element set, and the initial object is the empty set. And that's also the same in the category of posets. So does it reflect the initial, does it reflect initial objects? So that means if you land on something up there, if you start on something up there and its underlying set is empty, does that mean that this had to be the object? So the answer is yes, it did. So it reflects initial objects. If you started up there and you land on any one element set, so if you're a poset whose underlying set is has one element, then yes, you are a poset. So it does reflect initial and terminal objects. Group, however, does not, because oh, let me scratch that. If you start with a group G and you land on the empty set, well, there is no such G. This is not possible, because there is no group whose underlying set is empty. So I think that this might vacuously reflect initial objects, and I've never thought about that before, and I'm not sure if it's a helpful concept, but the reason it reflects them is that there is no way to land on the empty set. So there's a slightly more demanding thing that you can ask a functor to do, which is to create things, which not only means that if you land on it, you are already one. Let me try and get this definition right. I haven't thought about this for ages. I think it means not only that if you land on one, then you were already one, but also that there is one. So this would reflect initial objects, but not create them, because there is no initial object that lands on that. Top works the same way as posets. But if we think about reflecting coproducts, then something different happens. So if you take if we try doing co-products, what we're saying is that if we have a diagram in posets that becomes a co-product diagram in set, was it already a co-product diagram in posets? So let me draw a better diagram for this. So what we're saying is, supposing we have some diagram of posets, whoops. So this is the shape of a co-product diagram. And what we're saying is that if we look at the underlying sets, this is a co-product, which means, so this is the disjoint union of the underlying sets. So what we're saying is, does that automatically mean that this is a co-product? And the answer is no, because, for example, you could have the one element poset A and the one element poset B. If you take the co-product of those two one element posets, you should get a poset with two elements and no relationships between them. So if we put a relationship between them, so we say that A is less than or equal to B, that is still going to map to the co-product diagram, where we've got just the underlying set A and B. We have A here and we have B here, but this one is not a co-product. So this does not reflect co-products. Okay. Good. Next question, page 291 to 2. In the example of journeys to numbers for prices of the journeys, is the target category the monoid of numbers under addition? Yes. So that when you compose a journey, you add the numbers. So it's not the category where numbers are objects. Correct. Okay, good. Next question, page 294 to 5. I'm wondering if you could say more about what picks out means in the sentence, a function from any one element set to a set X simply picks out an element of X. Does it highlight that something exists which doesn't change the set it's picking out from, or does it take something out of the set which does change it? No, it doesn't change it. You're right. It just chooses it. So if you think about it, what is a function from the one element set? So here is this star, which is the one element I'm considering to be the one element of this set. And we've got a function from there into any set X. So what does it consist of? Defining such a function, what does it consist of? Well, we just have to say what this asterisk is going to go to. And so we have to say what f of star is. And that's an element of X. So defining any function like this is the same as picking an element of X and declaring that's the chosen element. So you're not removing it from X. You're just pointing at it. That's what picking means. So it's like, it's not even highlighting its existence. It's just choosing it. It's really going, this is the chosen element. And that's called a base point, where you just sort of label one element as the base point and then you're done. Okay, next question. Degenerately associating a single point to a quintessential category reminds you of the null object in group. Yes, the null object in group has only one object. It's the identity object. Would the quintessential single object category be a null object in category? Well, the single object category is terminal, but it's not initial, so it's not null, because it's not initial because you can have an empty category with no objects and no morphisms, which is different from when you have a group, because you can't have an empty group because a group has to have an identity element. A category has to have one identity element for each object, but if there are no objects, then it doesn't have to have any morphisms at all. Okay, so now we're back on this question about page 299, the square of forgetful functors. So the square of forgetful functors in question on page 289. No, it's not on page 299. Goes from rings where you can either, a ring has a group structure and a monoid structure. So you can forget down to the group structure, or you can forget down to the monoid structure. but both of them have to have the same underlying set. And so there were several questions about this. First of all, is there a pullback? What would it look like? And would you mind doing the proof alluded to in the second footnote? So the proof I alluded to is the proof showing that this is not a pullback. And the idea of that proof is that a ring is not just any old group on monoid with the same underlying set, because there has to be a distributive law. So what that is implicitly saying is that the pullback of these things would be, the objects would be a group and a monoid with the same underlying set and no further conditions. So you could have something like a ring that has a multiplication and an addition, but no distributivity over them. But more degenerately than that, you could just have a group and you could forget, this wouldn't be a forgetful functor then, it would just be the functor of the identity functor, and it would be, let me start again. You could have a group and you could take the functor sending every group to itself here, and then you could send each group to its underlying monoid here. Right? Now, so this is how we're going to show that that's not, let me see if I can do this. To show it's not a pullback, we have to show that there is some diagram that commutes where there is not a unique factorization. So what I'm going to do is put just the category of groups here, and I'm going to put the identity there and the forgetful functor there. So this, the outside commutes because here we're doing nothing and then taking the underlying set, and here we're just forgetting the inverses and then taking the underlying set. So the question then is there a functor from groups to rings like this that makes this diagram commute? Well, if you take a group, what I'm going to do is I'm going to take an example of a group in here that will have nowhere to go. So I can just take the smallest non-trivial group I can think of, which is the cyclic group of order 2 or the integers mod 2. So what would this functor have to do here? Well, it has to send it to a ring whose underlying group is, so this is the integers mod 2 under addition. So it has to send it to a ring whose underlying group is the integers mod 2 under addition, but whose underlying monoid is also the integers mod 2 under addition. And in order for that to be a ring, addition would have to distribute over itself, which it doesn't. Because if it were going to distribute over itself, you would have to say things like this. You'd have to look at that, and then it would need to distribute over itself. So we'd have to say that that equals 1 plus 1 plus 1 plus 1. And these do not equal. So this, there is no factorization here because there is nowhere for that thing to go. So that would be an actual proof that this is not a pullback. Now, I don't think that that proof is as illuminating as understanding why it's not a pullback, because the pullback should be things where it is a group structure and a monoid structure, and there is no constraint over how they're supposed to interact. So I think that answers those questions. Then there was finally a thing saying, is there a push out? So, oh, I think I better think about that for a second. I think this push out would be a bit strange. I mean, you can take push outs of categories. I don't know why you would want to take a push out of these categories, but what you basically do to take a push out of categories is you look at the objects first and you take the disjoint union, you do the push out of underlying collections. So these categories are not small, so we shouldn't say sets, but so you would take basically the disjoint union of all the groups with all the monoids, and you then need to quotient out by whenever some group is the underlying group of a ring, you kind of stick it together with the monoid that's the underlying group of the same ring. I don't know what this does. I think it's a bit weird. So that's my best answer to that. Not very conclusive, sorry. Page 301, does the set A have to be finite? So on page 301, we're talking about the free monoid on a set A. So what it says is given sets A and B, so they do not, there's nothing saying that they have to be finite, but the free monoid on it is the monoid of finite words. And the reason it's only finite words and not infinite words is that a monoid is defined by a binary operation. And by induction, you can use a binary operation to make any length a finite word, but you can't use it to make an infinite word, because every time you do the binary operation, you will just be sticking two elements together. And if you keep sticking two elements together, you'll never get an infinite word. So that's why it's only finite words, but there can be an infinite number of elements. On page 301, being a free structure is a type of universal property. Yes, because it's part of an adjunction, and adjunction is a universal property. If the universal properties can be expressed as an initial or terminal object in some possibly souped up category, how would you show this along the lines of how you did other universal properties using Cohen's? It's very, very souped up. And so, yeah, so the free, let's see, what can I say about this? The free, if you have a free functor, that's left adjoint to a forgetful functor. And usually it means you have some category of algebras up here over the underlying data down here. And it's not any old adjunction, but it's something called a monadic adjunction, which is universal among adjunctions. You can also construct left adjoints for things via a collection of universal objects inside a souped up category, which is a comma category. But this is all very far beyond what we have got to in this book so far. But that's basically the idea. It's around the fact that it's an adjunction, and an adjunction is a universal property. Page 302, question 1 of things to think about, 20.12. Could F be the free functor from monoids to groups? So things to think about 20.12 says, can you construct some very small examples of categories and a functor F in which certain things are true? And so no, F could not be the free functor from monoids to groups, because that is not an example of very small categories. And what I was trying to get you to do in this things to think about is to think about what it is at a very granular level that is going on. And I think that it's really important to be able to think about specific structures inside categories abstractly, rather than them having to have meaning. And so that's why I'm using quintessential morphism categories here, rather than giving them any meaning. At another level, if you mean, aside from the fact that it's not a very small category, there is a functor from monoids to groups, which gives the I wouldn't call it free personally. It's more like a group completion. It's also called a Grothendieck construction, but Grothendieck made so many constructions it's hard to tell which one is which so far. You basically add in all inverses that don't yet exist. So if you start with a monoid that doesn't have inverses, you can turn it into a group by freely adding inverses, but anything that already had an inverse should not get a new inverse. So if you start with a group over here, it will go to itself over there. And so I think what this question is trying to get at, because it's about something not being an isomorphism over here, but being mapped to an isomorphism over here. So if you take the natural numbers here, then they will get turned into the integers over here. If you take the integers over here, they will just stay as the integers over here. And so here we have an isomorphism, clearly, because it's an identity. Whereas here we have an inclusion, which is not the identity, and it gets mapped to that isomorphism. So that is an example of something that is not an isomorphism, that is mapped to an isomorphism. It's also another example of the whiteboard crashing again. And so I need to restart some things. But the idea is that it is an example, but it's not a very small one. And so that's not quite what I was trying to get you to do. Okay, I can barely even capture how frustrated I am that the whiteboard keeps crashing. And I'm wondering if it's something to do with the new microphone, which is plugged into the USB thing as well. The whiteboard never crashed before I started using this external microphone. So I've decided to try not using the external microphone and see if I can stop it crashing, because I am, in fact, going to scream if it crashes again. Okay. So next question, where are we? Can you give an example of how to use forgetful functors to help us with universal constructions? I think I already did. So that was the one saying that it's part of an adjunction. Forgetful functor, if it has a left adjoint, is going to preserve limits. So if you want to construct a limit in the big category, in the complicated category, you know that if it exists, then it will be preserved by the forgetful functor. So it should be that limit in the base category. So if you're sets with structure, you construct the limit of sets, and then you try and then you lift your structure up on the limit. This next question is quite long, but I think it's to do with the free and forgetful functors from monoids to sets. So we have a free functor, we have a forgetful functor, which is often called U for underlying. And what this question is saying is that if you start with 1, then that's only got 1 element. But then free of 1 is infinite. And so U of f of 1 is infinite. So what you've done is you've started with something very small, you've gone around and you've come back to something very large. And the question is, how can this asymmetry explain? Well, what is it that needs explaining? Why should there be any symmetry? These are not inverses. They are not pseudo inverses. It's just an adjunction. So we should not expect to come back to the same place. And in fact, it's very important that we don't come back to the same place, because this is how we make algebraic structure. So in general, what we do is we take a set, we go all the way around, and we come back to the free structure on its set. And then we look at, so this is according to the action of the functors. And then what we do is we look at functions from the free thing back to the original thing. And what that does is it tells us what the operations are going to be. So in the case of monoids, f of a contains all the operations that ought to have an answer in A. So it'll have things like A1, A2, A1, A1, A2, A2, A3, and so on. And we don't know what those are until we make a map from here into A, and that evaluates them in A. So it's quite important that we don't get back to the same thing, actually. Could we construct the natural numbers from n to begin with, and then we have a symmetry? No. So that then f of n is even bigger because it's words of natural numbers, and then you map them back into A by, so if we did this on, if we started with the natural numbers and then we get words in natural numbers, so that would be things like n1, n2, n3, and then the monoid action is addition. So if we have an algebra structure here, then what that gives us, it tells us how to add those numbers up. So in the free thing, it's like numbers we, in theory, should be able to add up. And then when we evaluate them in n in the algebra structure, that is telling us what they add up to. or maybe begin with any set of natural numbers which includes, does this make the monoid terminal in some sense? No, the natural numbers is not the terminal monoid because the terminal monoid has only one object in it. It's free. It's the free one-on-one. Yeah, I think that's all I have to say about that. Okay. Page 303, bottom of the page. How do you read the hooked arrow as a verb? Great question. Should I be reading it as hooked, as included into or included in? Yeah, you can say include. I might say includes. I might say includes, yes. Page 303, is the reason the two parallel arrows are different morphisms, is it that the objects in the quintessential category are not single elements, but sets of elements? No. The reason the two parallel arrows are different morphisms is because I said they were. So you can define morphisms to be anything in a category, right? And it's really important, again, and I will keep saying this, to remember that categories, the objects and morphisms don't have to have any meaning. They are just things. And so if I declare that there is a category with two objects and two different morphisms, that's it. It's got two different objects and two different morphisms. Doesn't have to be a reason. It is that way because it is defined that way. Page 304, is there a more abstract explanation for why epis aren't necessarily preserved by functors, but split epis are? I don't know what you mean by more abstract, but the reason is that split epis are defined by a commutative diagram, and commutative diagrams are always preserved by functors. That's kind of the whole point of functors. Whereas epis are not defined by their sort of higher order logic. Epis are defined by for all something, there exists something, or something is equal, right? For all pairs of morphisms going in such that, so you have, it's a very complicated definition that says for all something such that something is true. And definitions that take quantification like for all and exists, I think, as I said at the bottom of page 304, that for alls and exists change when you move to a different category. Because if you move to a category with more things, then for all becomes much harder to fulfill. And if you move to a category with less stuff, then there exists becomes harder to fulfill. I think that's what I said at the bottom of page 304. So yes, things that are defined by just a commutative diagram and no for all or exists are much more stable under functors. They have to be because the functor will always preserve the commutative diagram. Page 305, as long as the terminal and initial objects are different in both categories, will a forgetful functor preserve initial and terminal objects? No. This has come up a few times now. And so it's the same thing again, where if you have a free functor, it's left adjoint to a forgetful functor. A terminal object is a limit. And if you have a left adjoint, you preserve limits. So this one will preserve terminal objects. And this one will preserve initial objects. So let me see if I can think of an example. Okay, I thought of an example. It's a bit contrived, but it does do it. So if we look at the category of sets with two chosen base points and the forgetful functor down to just sets with no chosen base points, then this category is like a slice category. I haven't done slice categories, but if you've heard of slice categories, it's essentially the category of functions from a two-element set into another set. And so it's two, I can't remember how you write it, my brain's gone blank. Is it two down to set? Or is it two overset? Maybe it's two overset. Anyway, you can just think of it as sets with two chosen base points. So the initial object in here is the any two element set, because if you have any two element set, the morphisms in here have to preserve the base points. And so if you have a two element set and those are the base points, then you know exactly where both of those have to go. So another way of looking at it is that if you're thinking of it as functions from two into another set, then we're saying that the initial object in there is the function, the identity function, or the from the two element set to the two element set. So there are a lot of different two element sets. So you pick one. This is the identity, or a chosen isomorphism between them, I should probably say. And then given any function to x, there is a unique thing here making this commute, because you just go along the inverse here and then along here. So the initial object is the set with two elements, and those are the base points. But the terminal object is the one element set where both chosen base points are that one element. And so then this forgetful functor will take the terminal object to the terminal object, because it will take the one element set to the one element set, but it will not preserve initial objects, because it will take the two element set here to two element set there, which is not the initial object. So this is a counterexample. So this is an example where the terminal initial object are different, and the forgetful functor does not preserve the initial object. Could you please unpack the things to think about 20.16 and explanation a bit more? Page 305. Questions like that are very hard to answer, because you haven't given me an indication of what it is you don't understand, and therefore what it is that needs unpacking. So 20.16, in chapter 18, we saw that various products of sets with structure do have the product of sets as their underlying set. Can you express this in terms of some functors preserving products? So what that's saying is that if we have sets with structure, and we're forgetting just down to sets, then if we start with a product up here, and then we forget down to here, we're saying that the underlying set of the product kind of was the product of the underlying sets. Now, really, we should draw the entire product diagram, but with its projections as well, but this will do for now. So that's saying that U preserves products. And now consider the examples where the co-products and pushouts did not just have the underlying set, the product of their underlying sets. Well, that's saying that we took A plus B and we went to U of A plus B, but this time it was not the co-product of the underlying sets. And so this is not preserving products. I think that's pretty much what I said on page 305 though. So maybe some symbols, maybe it's just some symbols that help. And then the last question, I confess I'm quite confused by, it says, how do you resolve the problem that pi1, the fundamental group functor, doesn't preserve the thing you actually want, i.e. map homotopy equivalences to group isomorphisms? Pi1, I think, does map homotopy equivalence to group isomorphisms. Inside algebraic topology, that is called being what's it called, being homotopy invariant. So the whole point about the homotopy groups is that if we're trying to study spaces X and Y and a homotopy equivalence between them. So what that means is that there's something going in this direction and something going in this direction, but they don't compose to the identity. GF is homotopy equivalent to the identity on which way around is it? X probably. This is, yeah. And F, there's a homotopy from FG to 1Y. And so what that gives us is that when we take the fundamental group or the nth homotopy group for any dimension n, it definitely turns into an isomorphism, I thought, of those groups at every level. The problem is the converse, which is that just because you have an isomorphism of homotopy groups at every dimension does not mean that you have a homotopy equivalence. So they are homotopy invariant, which means that if two things are homotopy equivalent, they produce the same answer, but they do not detect homotopy types, which means that they can't always tell when things are different. And so that, I think, is the difference. So you could have all the same homotopy group, isomorphic homotopy groups, but still not be homotopy equivalent. I think that is the case. I'm not an algebraic topologist, but I think that is the case. So I think that's the last question. Woo, that was a lot. That was a lot. Praise and joy, praise for Joy of Abstraction. Thank you Topos Institute. Thank you, anonymous classmates. That's nice. So grateful for this book club. I'm so glad. It's getting quite a lot now. I really enjoyed this chapter. Good, great book. Hope you'll consider writing a part 2. Crikey. And thank you for being so helpful. Well, thank you for asking such detailed and deep questions and for still being here. I will look forward to seeing you next time for chapter 21. We're down to the last few chapters now, so that's excellent. Thanks, Topos Institute. Thanks, everyone. Bye.